I'll do this in English since we have several members that are on the committee that are English speaking only. So, and we have Emiel from abroad anyway. Huh?
Right.
We're being from Belgium. And the Flemish part, which is kind of far away, I suppose. Huh?
It's all right. It's all right.
Okay. So you find yourself here in the Department of Mechanical Engineering. You know that because otherwise you wouldn't be sitting here. And mechanical engineering is about everything that moves. It's different than electrical engineering. That's about charge that moves. We have look at real things that move. But you're in particular here in the Center of Systems and Control. And systems is a general way of looking at movement, whether it's electrical or mechanical. And furthermore, you are in the group that we call economic engineering, and we look at another type of movement, which is the movement of goods. And as a force causes a movement of masses, prices and their changes cause movement of goods. And this is the domain of economic engineering, so it's really engineering, and that's the domain where Emiel will be holding his presentation in right now, and afterwards his defense. So this group is we feel very exciting group, and we're doing all this nice stuff, and we felt we were pretty exciting people until Emiel showed up. All right, so Emiel broke all our prejudices and preconceptions of what it means to be exciting. And in particular, as a scientist in particular, all our prejudices we may have of our southern neighbors here. So he showed up and he changed everything. So although we're interdisciplinary, Emiel went ahead and brought in a lot of what we will call scary stuff, which is advanced math. You know, if you're not in engineering, you may think this is part of parcel of what we do. No, we get very scared by this. So this is, I'm not going to say much about what he's going to present. That's up to Emiel, but I will tell you that we have a large committee consisting actually of 5 individuals. And this is because he is so broad in his applications. So we have somebody from Utrecht, Rogier, who is in the pure math department, and so knows everything about the mathematical aspects. We have Tamas, who is a real systems person, and then we have myself, Koen, and Dimitris, who are really interested. Dimitris is particularly interested in applications of this to engineering in general. So with that, I think my time is up, and for you to continue and live up to the expectation of breaking all expectations and barriers.
Right.
Emiel, please.
Right. Thanks a lot, Max, for the introduction. So my thesis is titled "The Geometry of Dissipative Mechanical Systems Using Jacobi Manifolds and the Split Quaternion Algebra." Now, it may not be entirely clear to you yet what geometry has to do with mechanics and why it is so important, but I will try to explain to you today why this relation is so close and why it is especially important for systems that exhibit dissipation. So let's talk about mechanics first. Now, you're probably familiar with Newtonian mechanics. So that's the bread and butter mechanical formalism that everybody, or at least the engineers, learn in their first year at university, and you use vectors and forces and accelerations to establish the equations of motion. But there is an alternative formalism, or there are 2 actually, and those are called Hamiltonian and Lagrangian mechanics. And well, they end up with the same result, but they get there differently because they start from an energy representation of the system rather than all the forces and the vectors. And then you apply Hamilton's equations and out come the equations of motion. And although this is usually considered to be a more advanced formalism, I will try to make the case today that it's actually preferable also for practical purposes. And to make that case, I give 3 reasons. First of all, as Max already told you, we are here at I wrote my thesis for the research group Economic Engineering. And the people at Economic Engineering, what they try to do is they try to apply the same tools that we use for traditional engineering applications to economic systems as well. And how they do that is by establishing analogies between the mechanical domain and the economic domain. And for example, we would say that momentum is analogous to price, position is analogous to quantity, and energy is analogous to profit. And as it happens, the Hamiltonian formalism is exactly expressed in these 3 quantities. And that is actually why in economic engineering, it is the Hamiltonian formalism that is the most intuitive. So because I mean, I don't know about you, but if you ask me what are the most fundamental quantities in an economic system, I would say price, quantity of goods, and profit, right? So the Hamiltonian formalism is a very intuitive way to look at economic systems. The second reason is already, as I already told you, the Hamiltonian formalism is energy-based. So no matter how complicated the system is, you just start with the energy expression, which is usually fairly easy to set up. And you apply Hamilton's equations, and out come the equations of motion. So even for super complicated systems with many different components, and especially economic systems, they can get very complicated. It is still very easy to apply the Hamiltonian formalism. So especially for very complex systems, this Hamiltonian formalism has a huge advantage. And then the third reason, we're already, like was mentioned, we are here at the Department of Systems and Control, and there is a control formalism that is called Hamiltonian systems. It's deeply rooted within the Hamiltonian formalism. So if you want to use this, and we do, especially at economic engineering, then our system better be cast already in the Hamiltonian description. So that is why it's already beneficial to model it that way too. So this, of course, begs the question, why are we not using Hamiltonian mechanics all the time? And the reason for that is very plain. Hamiltonian mechanics, in its traditional form, does not support dissipation. So if your system does not conserve energy because of friction or air resistance or any other reason, or in an economic context, you have expenses that you cannot model directly, like additional costs that you incur if you move through the economic space, then Hamiltonian mechanics fails to give you the correct description of the system. But this was actually the goal of my thesis, to solve this problem. And the goal is to develop a Hamiltonian description that inherently captures dissipation, so part of the system itself. And to do so, there are 4 factors that are super important. And the first one is that we need to keep track of the dissipated energy. So normally Hamiltonian mechanics would only consider mechanical energy, but now we want to keep track of the dissipated energy too, to capture the entire story. And in the economic context, you would say that we need to count the expenses too, right? You have your profit, but you need to subtract from that gross profit. You need to subtract your expenses in order to get the net profit, which is what is actually important. The second thing is that I've merged the thermodynamic and a mechanical viewpoint in order to arrive at the correct solution. Third is that I looked at the underlying geometry of Hamiltonian mechanics in order to find the problem, because only looking at this underlying structural formalism, you could see what was actually the problem. Because, I mean, you can look at Hamilton's equations and, okay, it doesn't work for dissipation, but why that actually is a problem, you can only see if you look at the geometry. And the fourth one is that we want this formalism to be applicable to for engineering purposes. So nothing too mathematical, we just want it to be readily usable for any practical applications, be it mechanical or for economic systems. And the answer to that, I make the case, are Jacobi structures. And I will explain to you what those are in this presentation. So first of all, let's talk about what goes actually wrong with traditional Hamiltonian mechanics, because I mentioned to you, it doesn't work for dissipative systems. So let's investigate why that is the case. Now, the reason is that traditional Hamiltonian mechanics are based on symplectic geometry. And symplectic geometry is the geometry of the phase space. Phase space being space of momenta or positions, or in the economic context, the space of products and prices. So it's a very natural setting to be in if you want to model economic systems. And well, the space is always even dimensional because every product has its price and they also belong together, right? You always have a pairing between a product and a price. You cannot just mix those up. And the symplectic structure, we call it omega, exactly does that. It just pairs the product and its associated price, or in mechanical terms, it's the position with the associated momentum. And this symplectic structure gives us a notion of oriented area. And in economic engineering, it's even easier because if you multiply a number of products with their price, you get a piece of value. So especially in economics, the symplectic structure is a very compelling interpretation. Now, the second ingredient that we need to set up Hamiltonian mechanics is the Hamiltonian itself, right? The mechanical energy in the system and mechanics. And in economic systems, you would say that is equal to the profit of the system. And then using that symplectic structure, you can find a relation between the gradient of the Hamiltonian and the Hamiltonian vector field. And that just tells you how the system will evolve in time. And I can illustrate that with a very easy example. It's called the harmonic oscillator. You probably all know it. And in economics, we would say, okay, this is sort of analogous to a trader of some sorts. You have a mass that gives you a relation between the amount of product that is moving and a price. So that's like a supply and demand relation. And the spring, which gives you a notion of storage costs. And the interplay between those components gives you this oscillating behavior. Now, if you look at the gradient of the mechanical energy, it looks like this. It's a star-shaped vector field, or the gradient of the profit. It tells you in which direction you need to go in order to increase your profit. You can increase price or increase product or a combination of either. And what the symplectic relation does, now you can see this angle here on the left, and you can take it quite literally, because what it does, it rotates this gradient field by 90 degrees. And you can see that actually you're always moving perpendicular to your increase in profits. That is to say, your profit always remains constant. If there's no additional expenses, you will remain operating, you will keep operating at the same profit level. And then you get these circular trajectories that we know from the harmonic oscillator. Now, what happens if we include dissipation into the system? You can see a little damper there. And in in economics, we would say that is analogous to some sort of additional expense that you cannot simply model, like a transaction cost or a form of consumption or anything like that, something that you pick up along the way and you need to keep track of. And what happens then is you get these spiral trajectories. You do not remain in this circle, and eventually will approach the origin as the mechanical system comes to a standstill, or the economic system runs without profit. And if you look at the vector field that goes associated with that, you can see that there is like a sink present in the origin that draws the dynamics towards the origin. And if you then would apply that symplectic mapping, that rotation, you can actually see when compared to the original gradient that there's a little tilt to the right. And that tilt, that says that this vector field has a curl. And a vector field with a curl can never have a potential function. But we need this potential function in order to have a Hamiltonian. So that demonstrates why we will never be able to find a Hamiltonian description for a dissipative system. Now, this has been a long-standing problem in the past, and some people have already worked on it. So I'll go over a few past attempts first. So the first thing is the non-physical Hamiltonians. And those are people that really try to find the potential function anyway by like somehow cheating a bit. And you can see here, they come up with this very weird function as like logs and cosines and whatever. And well, it does manage to give you the correct equations of motion, but it does not represent the mechanical energy or the profit in the economic system. So, I mean, that sort of defeats the entire purpose, because if I give you a different system, then and ask you what the Hamiltonian would be, there's no way to know, because you wouldn't know what the Hamiltonian would be for that different system. Now, there's a second approach, which are time-dependent Hamiltonian functions. And an example is the very famous, or at least within the field, Calderon-Lacanai Hamiltonian. And well, this does work. I mean, it gives you the right equations of motion, and it represents the mechanical energy, but it does so by cheating, because what they do is they just build in the time dependence that arises from the dissipation in the Hamiltonian function. So what they do is they say, okay, we just treat these expenses as something exogenous, as something that we cannot control, that is not part of the system itself. But of course, like expenses in an economic system or dissipation in a mechanical system are endogenous. They are part of the system itself. So I do not find this approach completely satisfactory. So that is why we move to contact Hamiltonians. And with contact Hamiltonians, that's also the approach that I worked on. We recognize that, well, symplectic geometry, as I mentioned, is simply too restrictive for dissipative systems. It simply cannot work. So what we need to do is we need to modify that underlying formalism in order to make room for the dissipation to occur. And well, there have been attempts for mechanical systems. They have been partially suggestive. I mean, like it sort of works, but also not. But it has also been applied for equilibrium thermodynamics with very good results. And one of my contributions is that I managed to merge these two approaches in order to construct a suitable contact Hamiltonian formalism for dissipative systems. Right, so how would this work? Contact geometry is based on contact manifolds, and you can think about a contact manifold as a symplectic manifold with one extra dimension. So the symplectic manifold, as I told you, is the pairs of products and prices in the economic space. And this one extra dimension we need to keep track of the dissipative energy or the expenses that you have, right? So we need this one extra degree of freedom just to keep track of what we're losing along the way. And so we express the system dynamics in these coordinates. Now, on this contact manifold, you can then construct or define a contact structure. And that is basically just a collection of hyperplanes, as you can see on the right. And what these hyperplanes are, they're just a non-holonomic constraints. You can think about them like that. So they sort of these hyperplanes, they push the system as it moves along in the space in a certain direction. And this constraint needs to be satisfied. And that constraint I took to be the first law of thermodynamics. So conservation of energy. And the first law says that, well, the change in energy is equal to the heat added to the system minus the work done by the system. Now, we don't have any heat, so we just have work because the system is performing work on the dampers. So that is what we're going to model. And if you would state that mathematically, you can do that by means of a contact form. So that's the alpha that you can see here. And what we say is like, okay, a small amount of dissipated energy U should always be equal to, well, the work done on the dampers. And in the case of a damped harmonic oscillator, that's gamma P times dq, right? Gamma P being the force, dq a small amount of distance. Or in economic terms, you can see this like a bit of a transaction cost, right? You multiply a fraction of the price times the number of products that you move. And these transaction costs you need to accumulate in your expense account, being du. So what this says, it basically just restricts our system to being conservative, really. So for a mechanical system, how does this work? First of all, we have the Hamiltonian function k. We call it k now instead of h, just to make the distinction. And that is proportional to the total energy, so being the mechanical energy and the dissipated energy, whereas before we only would have mechanical energy. In economics, you would say this is the net profit plus all the expenses, being the gross profit. Then the second ingredient is that contact form that I showed just now, being the work done by the dampers, or that describes how you incur these expenses as you move along the economic space. Third example, the third ingredient is a 2 form that is the exterior derivative of alpha. And this gives us exactly that symplectic pairing between the prices and the products, or between the positions and the momenta. And if you do that, then you can actually construct the contact equations of motion. So you can have this symplectic mapping, and you have the gradient of the Hamiltonian on the other side, but you correct the gradients for the dissipation occurring, right? So you can see this as like gradient of the gross profit, and you subtract from those the expenses to get the gradient of the net profit, because the net profit is what is important for the economic system. So just to show this graphically, we can have the gradient of the mechanical energy, but then you apply this correction term that exactly tells you how much work is done by the dampers, and that actually gives you the gradient of the net profit, or of the sort of the net energy, if you will. And if you then apply that rotation by the symplectic mapping, then you arrive at this vector field with the sink and the spiral-like vector fields. So that is like a geometric picture of how this works. Now, I mentioned that we are actually working in an all-dimensional space, and I'm showing you a plane. So where is the extra dimension for the dissipated energy? And well, you should really look at the system from a 3-dimensional perspective, and then you see that the spiral that I showed just now is actually a 3-dimensional spiral, with the height being the dissipated energy or the expenses incurred. And then we also have a third equation of motion. We have 2 equations for position and momentum, and 1 equation for the dissipative power. How much power is generated by the dampers at any given time, or how much expenses are you incurring at any given moment in time. And this is actually a restatement of the first law of thermodynamics, because any work done on the dampers should enter the dissipated energy, because otherwise energy is somehow still escaping the system, and that is not what we want. There's also a second law of thermodynamics, otherwise it wouldn't be called the first one, of course. So, and what the second law says is that the dissipated energy, or the entropy, should always be increasing. And you can see the dissipated energy as a proxy for the entropy, and I can explain to you why. If you would look at like an infinitesimal amount of potential energy, that would be kq dq. An infinitesimal amount of kinetic energy would be p over m dp. So you have q and p and p. But then if you look at dissipation, you see, well, I have a p and then dq. So you mix them up, right? You mix the energy from potential and kinetic energy, and you lose this distinction between energy stored in p and energy stored in q. And because you lose this distinction, this energy is actually lost irreversibly. You can never get it back to do anything useful with. And that's the whole point of dissipation. So you can see that the disorder in the system is somehow increasing, which then again is a manifestation of the second law of thermodynamics. Now, in economic engineering, we would say, okay, when we have these expenses, I mean, they reduce our profit, but they're somebody else's profit, of course. I mean, somebody else is making a profit on our expenses. So the profit doesn't disappear, it just goes to other people. So we call this process the diversification of profits, right? So our profits just get diversified away in degrees of freedom of the economy that we did not model. You can also see that equilibrium is reached when the dissipated energy U is maximal. Right, okay, so this is great. We have this contact Hamiltonian formalism, works for dissipative systems. Now we can make the link again with literature. So I mentioned that people have tried contact Hamiltonian systems before, and it sort of worked. I mean, like some parts were suggested, but other parts did not work. And the reason why that went wrong is because they didn't have the interpretation for the contact form to represent the first law of thermodynamics. And only if you do that, you see that this contact form actually applies as a restriction to the system, and it restricts the system to what is called Legendre submanifolds. You can see it there, it's sort of this mountain in the three-dimensional space where the trajectories must all be on, because otherwise conservation of energy is not satisfied. And only if you do that, the equations of motion, like the spurious terms that the people were all confused by, they fall away, and you get the correct equations of motion for the system, 2 for position and momentum, and 1 for the power. So that's already one contribution with respect to the literature. Secondly, we can also make the link with the time-dependent systems that I discussed. And we can do so using a process called symplectification. And what symplectification does is it allows you to write a contact Hamiltonian system, again as a symplectic system, by raising its dimension by 1. So we started off with like 2 dimensions, just P and Q. Then we added U, that was 3 dimensions. And now we add yet another dimension. And that allows us to make it symplectic again. And the way you do that is by exploiting what we call like a multiplicative symmetry. So if you imagine the first law of thermodynamics is just an equation, and you can multiply that equation by any non-zero factor, and it just remains just as true. It tells you the same thing. And this ambiguity that you can exploit, and you can put it in a separate dimension. And that is the 4th dimension that we need for symplectification. And this multiplication factor, it takes the form of some kind of fake momentum. And especially in economics, it has a very compelling interpretation. And you could say that it is sort of equal to 1 over the discount factor, because it has this exponential form, with gamma then being the discount rate. And also it applies to our original momentum in a way that it actually sort of, it reverts our momentum back in time, or it's sort of like you would use a discount factor when you compare prices at different points in time. So there's sort of this, it uses this discount factor to, well, to discount the momentum or the price really. So if you do this, you get 4 equations of motion. You get 2 for the momentum. One of them is actually the fake momentum that you can see there. It's not really an equation. You can just see it recreates that exponential behavior, right? You get the changes proportional to itself, and that just recreates that exponential term, and you can use that to model the dynamics. And 2 more for the position. Now, why is that good? Well, because if we do this, if we simplify the contact Hamiltonian system that I proposed for the damped harmonic oscillator, and then project it down again, you end up with the Caldirola-Canai Hamiltonian, which was that famous example of a time-dependent Hamiltonian that has been used many times in the past to model dissipative mechanical systems. And this is great because, well, it has this very weird shape. I mean, there's like these exponentials lying around all over the place. You have a different momentum coordinate, and the physicists, they use it, but they didn't quite catch what was the explanation behind the specific form of this thing. They knew it worked, but there was no interpretation for it. And using this symplectification procedure and also the economic interpretation that we have, you can actually explain very easily how this thing comes about. And you can also see that, well, the Hamiltonian is a profit, is a cash flow. So the Caldirola-Canai Hamiltonian is actually just an example of a discounted cash flow, which is a very common practice in finance. All right, so I did promise you that my formalism would be applicable to any mechanical system. And unfortunately, with contact Hamiltonian systems, that is simply not the case. But this is also where it gets really pretty, because we have been like sort of thwarted by the mathematicians who came up with the definition of contact, because they said, okay, we want this d alpha, the symplectic structure, must be the exterior derivative of the contact form. But, well, conceptually, I mean, contact form gives us dissipation or the expenses. Symplectic form is at least supposed to give us the pairing between position and momentum. But inherently, these things have nothing to do with each other. Like, it's just 2 things that you need to impose on the system separately. And somehow we still need to try, we still want to try to derive one from the other, and that's somehow not possible. So for general systems, like the one you can see on the right, you have these 2 masses, and then again, it's like for this system, it's not trivial to couple the momentum to the position, because there's 2 momenta and 2 positions, and you can sort of couple them in different ways. And because of those dampers in between, if you take the exterior derivative, that goes wrong. So we need an extension, and those are Jacobi structures. And this is just a slight generalization of a contact structure, but it does allow us to choose that omega separately. So we can choose our own symplectic structure. And then we have 3 completely separate ingredients. We have the mechanical energy, we have the Hamiltonian, the contact Hamiltonian K, equal to the total energy, mechanical plus dissipated. Or in economic terms, the gross profit, the expenses plus the net profits. Second ingredient, the one form alpha that says that governs dissipation, tells you how much work is done by the dampers, or how the expenses are generated if the system moves along the economic space. And the third ingredient, the two form for the pairing between the products and the prices, or the momenta and the position. And this, I will promise you, works for any system, any mechanical or economic system that you give it will always work. And I can demonstrate that to you. Like equations might seem a bit daunting, but just like we just want to get an idea of the general picture. So for the system, we just start with the Hamiltonian. So we have dissipated energy U, or the expenses, and then we have kinetic plus potential energy. So it's fairly easy, just look at the masses and the springs and you're done basically. Then we have alpha, giving us the work done on the dampers for the first damper, and then for the second damper, or the expenses occurred by the economic system that is analogous to it. And then if you do that, you can just apply the Hamiltonian equations for this Jacobi structure and outcome the equations of motion. I have one for position, I have one for momentum with all the damping forces attached to it, and I get one for free, being the power dissipated by the two dampers. So that third equation really is an inherent part of the entire Hamiltonian system. You get it for free, basically. Right, so to conclude, I developed a practical Hamiltonian formalism that you can apply to any mechanical system, or an economic system for that matter. And you reduce a system basically to a single energy balance that tells you how energy is leaking out of the system. And then if you apply, well, then the structure will just do the work, because the Hamiltonian equations give you the right equations of motion. And importantly, you get equations that are both energy and force based. So you not only get equations for position and momentum, which would be the traditional fashion, but also for the dissipated power, you get one for free. And this method, actually, I did not mention, has a very close relation with bond graphs. That is a way of modeling that we use in economic engineering. And it's a very systematic way. And this, the method that I propose, has a very deep relation with these bond graphs. So for economic engineers, it's extremely easy to use them. Second conclusion, I unified this framework for the mechanical and the thermodynamic viewpoints. And that means that you can also add thermodynamic elements to your mechanical system without any added complication, right? So you can add like ideal gases or pistons or any kind of thermodynamic component that you want to the mechanical system. Thirdly, this geometric structure has a physical and economic interpretation. And that is very important because we want to know what we're doing when we want to apply this to a real system, right? And you can also see that because of this interpretation, like, remember what I told you about the Legendre submanifolds? We can actually see what went wrong in literature when people just try to apply this blindly. And then finally, our simplification also provides a link with past attempts in literature using that time-dependent systems. Now, why is this great? Well, I made a foundational framework for mechanical and economic engineering. So anyone who wants to model any complicated mechanical or economic system can just use my formalism, and the equations of motion, anything will just come rolling out very easily. So it's a very convenient tool for modeling in future research. Well, and if you have that model, then you can apply the port Hamiltonian control formalism, because the system is already cast in the Hamiltonian description. So you can just readily use the control methods that are specifically designed for that formalism. And finally, I did not go into that in my thesis, but it's a very interesting result that I obtained. By looking at this underlying structure of these systems, I managed to come up with a different representation for dynamical systems. Usually you would use like a matrix or a transfer function, but I actually used a different number system. They're called split quaternions, and you can use those to represent dynamical systems in a super convenient manner, because various very important aspects of the dynamical system are directly represented in this split quaternion representation. For example, just to give you a quick example, if you would want to classify a dynamical system as a saddle, a source, or a sink, or anything like that, it's just directly reflected in the structure of the split quaternion. And that concludes my presentation. So I thank you very much for your attention, and well, I hope you find it interesting.
Allowing us to share this with you. And the audience probably came here thinking they were just going to kick back and relax and see Emiel perform. But that's not the idea here. You are required to participate, especially if you know nothing about this. After this presentation, there'll be a defense, and then we will start asking our types of questions. But what I'm really looking forward to is just regular questions from the audience, like, I have no idea what you're talking about, please explain. So with that, any questions? Yeah, I think you were slightly earlier.
Exactly, split quaternion.
Right. So that's a very good question. I actually also have a slide about that. So split quaternions, they are you familiar with like normal quaternions? Yeah. Yeah, right. So it's a four-dimensional number system. You can think about it as like complex numbers, but instead of an I, you also have a J and a K. So it's like a four-dimensional number basically. And well, they form their own little algebra where you can do multiplication and addition. And well, you can use, well, and it looks like that. So it's just four components. And there's like specific multiplication rules for, so if you would want to multiply two split quaternions, just distribute them. And the individual components, so I, J, and K, and 1, they multiply according to that table that you can see there. So those are the rules. But what is interesting about that is that this algebra of split quaternions is actually the same as the algebra of 2 by 2 matrices. So they're somehow equivalent. You can just say anything about matrices or say the same thing about split quaternions. So usually we represent dynamical systems by matrices. And what I did is, okay, I used this equivalence between the algebras to look at the dynamical systems as split quaternions instead. And if you do that, then it turns out to be very convenient way to look at the dynamical system.
But so like the difference between classic quaternion and split quaternion.
Oh, is in the multiplication rule. So that's a very good question, and it's actually in these two minus signs. So if for normal quaternions, the J and the K, if you square them, they also square to -1, just like the imaginary units. But here the J and the K, they square to 1. They're not real numbers, so it's not just 1. I mean, that would be too easy, but they square to 1. And that's actually the reason why the whole thing is split, because this difference in sign makes the behavior sort of different. It makes it possible to see it in different regimes. Does that answer your question? Right.
I saw, yeah.
First of all, thanks for the presentation.
Right.
I had a question about slide 10. You briefly mentioned bond graphs.
Right.
I was wondering what these are. Let's
right.
Maybe use it in the presentation.
Yeah, so a bond graph is what we call a multi or a domain ignorant way of modeling. So you can have like an electrical system, a mechanical system, a hydraulic system, or a thermodynamic system. You have all these kinds of regimes. And a bond graph is like a general way to model either of those types of systems. So to give you an idea, in electrical engineering, you have resistors, and they are analogous to dampers in the mechanical domain. And masses are the same as like an inductor, so like a coil, and a spring is analogous to a capacitor. And these three elements you use in bond graph modeling to set up the equations of motion across different domains. And you can see why this is useful for us, because we want to use the analogy. So that's why bond graph modeling is super convenient.
Okay, that's clear.
Yeah. Okay.
Further questions?
Online or yeah.
Yes.
No question.
Thomas.
A general question about economic engineering. So you talk about quantities of products,
Right.
as a fundamental element, but how would one think about extending this to services or?
Well, there have been works about that in economic engineering in the past. So what people would use, for example, I think in services, they would use like an FTE as the product, just like a full-time equivalent amount of labor, basically. Or you can use, well, there's a different approach that goes in the world of finance, and that says that capital is actually a position. So you use capital, you have like an investment, then on that capital you generate the profit. So then the money itself is also a product, really. So it's a very, how should I say, it's a very flexible framework. You can apply that to very different kinds of things.
In your approach, could you extend this to cases where, let's say, your mass would depend on positions, or if the
yes, totally.
Your price was dependent on stock level?
Yes, especially because like in particular, the Hamiltonian formalism is very well suited for these types of systems, because then the forces get quite involved, because well the masses are dependent. For example, if you would have like a double pendulum or something, but in Hamiltonian mechanics, the energy is still pretty easy to set up. And then the derivatives generate all the forces that you need. So especially for those kind of systems, this is a very convenient framework.
Thanks.
Other questions?
Well, if they're not, then
Right.
I think we should